As parameter measurements used in this instrument, I like to characterize its output signal. This unit does boast a 120 microsecond per point sweep rate, which means it does have a very fast synthesizer. I'm also interested in taking a look at the quality of the signal coming out of the port, because if it does have a good synthesizer, you basically have a 6.5 GHz tunable synthesizer as well, which you can use on either of the channels. So there is some advantage to that, of course. And it does provide up to 10 dBm of output power, which is quite good. So let's take a look at the output here. This is directly connected over here to our Signal Hound SM200C, which is a 20 GHz real-time spectrum analyzer, a phenomenal instrument itself. I have done full teardown and reviews of multiple of their units on the channel, so you can take a look. Now, by doing this, we can look at the signal in real time as well as do various types of sweeps directly on the network analyzer and see the quality of the waveforms. And here's the software interface of the BN100 Plus. It's a very simple GUI with a very familiar interface. So if you've used pretty much any network analyzer, you should be able to very easily find your way around. So right now we're sweeping from 300 kilohertz all the way up to 6.5 gigahertz. And even though it doesn't look like it, the waveform is actually updating. Now at the same time, I have the GUI of our Signal Hound also running, but it is in pause mode. Now as the instrument sweeps, the input impedance of the actual spectrum analyzer is going to change as various switches come and go across this. Now this is a very, very fast instrument. So if I put it on auto mode, you can see we're catching the actual sweep up to 6.5 gigahertz. So the entire sweep only takes about 33 or 32 milliseconds. Now if I go back to our network analyzer, you can see the waveform changing as we sweep, and look at how fast it is. This might be one of the fastest update rates I've seen on a network analyzer, certainly through a USB interface, because it's a 120 microsecond per individual measurements, which is quite impressive. Now we can go ahead and change the sweep type and take a look at the waveform directly on the spectrum analyzer. And here now I have both of the GUIs side by side. Makes it a little bit easier to navigate. Now in order for us to investigate the signal, we want to change the sweep type. Now it does have a few different sweep types: linear frequency, logarithmic frequency, a segmented where you can enter on a table the points you want to cover, and a power sweep. There's no CW, but we can emulate that effect by changing the span to 0. So if I go over here and choose span, I can set the span here to be 0. As soon as I do this, the start and stop become the same, and that allows us to basically create a single CW tone, and it does that reasonably well. Now as the spectrum analyzer sweeps across the frequency, as soon as it hits the 3.25 gigahertz, which is the center frequency here, we do see that the S11 gets really good, which is the job of the spectrum analyzer. So this is all normal. So let's change the start and stop, or rather change the span. Let's put it at 1 gigahertz here, and we can actually change it using this. Let's go all the way down to 100 megahertz. And at 100 megahertz, we do have a lot of harmonic as to be expected. The waveform here is sitting at 0 dBm, by the way. We can go ahead and try and change that. If I go, for example, to power here, you can see the power is at 0 dBm. I can reduce the power, and it does a pretty good job at maintaining that. So it has minus 20. You can see we're reading minus 20.5 or so, and the THD remains constant pretty much across, which means it's generated earlier in the chain of the synthesizer. So let's go all the way back down to 0, because 0 is what I'm interested in trying this out. And we can change the frequency now. Okay, go back to the span over here and change the center frequency, go higher. And as we go, various aspects of the THD will change, different waveforms come and go, so you can see the THD will at some point get quite good. Like for example here, the THD is pretty reasonable. We do have an outlier tone here, which is actually outside of the frequency range of the synthesizer. If I create a marker, you can see that's sitting at 7 gigahertz, so it's above 6.5. Again, it has to do with how the power amplifiers and the synthesizer ends are designed. And as you go on higher and higher frequency, things of course get better, and here is 6.5. You do have a little bit less output power, but we also have more losses in the cable, so that's normal. So here we can go ahead and change the power again and see how high we can go here. And this is going indeed 1-to-1, and here's 10 dBm minus 8.6, so it maintains the losses. There's a few additional tones sitting around the signal over here. Probably the synthesizer has some unwanted tones. It probably doesn't matter so much in a network analysis mode, but it's good to see that it does create a reasonably clean signal at these higher frequencies too.